Now we start the first of two lectures dealing with larger scale objects in space, and today we will look at the Milky Way Galaxy. So what is this band that we see up in the sky? As you can imagine, ancient humans weren't really sure what they were looking at. There are stories in mythology that what we observe to be the Milky Way and how it got its name was because of the fact that it was thought to be the milk from Hera, which sprayed into the sky. And that name from that story has stuck with us even to this day. Obviously, we know today that the Milky Way is not comprised of milk, but instead is comprised of billions of stars. And it turns out that our sun is one of many of these billions of stars and in the Milky Way, and it exists actually not very close to the center at all of the Milky Way. But how did we get to know what it was that we were seeing? Once astronomers started to try to tackle this problem, they began to try to map out what we observed as this band going across the sky. William Herschel attempted to map out what he saw, and he deduced incorrectly that the sun would be probably pretty close to the center of this collection of stars. So in these days, it wasn't known that there were other galaxies out there. So to scientists and astronomers of this time, this is a mapping out of the entire universe since they are not aware of the other galaxies. And so there's a tendency for us humans to think ourselves important, and maybe that clouds our judgment as to where exactly would the sun be located in the universe. Well, maybe somewhere near the center. And so actually we know that this is not at all the case. But we can figure out something about how the Milky Way Galaxy is shaped, even if we can't go outside of the Milky Way Galaxy and look back at it from afar. How we can deduce that is by figuring out what things would look like if the Milky Way were different shapes. If the Milky Way were the shape of a ball or a sphere, then we would expect about as many stars in any direction that we would look. But instead, that's not what we see. And instead, if the Milky Way were more like a disk, then we should see a band where the most concentrated part of the stars, distribution of the stars, lies. And that is actually what we observe, so it's sensible to deduce that the Milky Way is a disk-like shape. Kapteyn tried to improve upon Herschel's original mapping out of the galaxy. Again, this was called Kapteyn's universe because, like I said earlier, we didn't know that other galaxies existed at this point. So he thought he was mapping out everything there was. And so he used more modern equipment and got maybe a little bit better handle on the fact that this is a very large structure, but obviously not anywhere near what we actually know is the size of the galaxy. And also he placed the sun fairly close to the center. So it was an improvement, but it still suffered from a lot of the same problems as Herschel's model. It wasn't until Shapley came around that we figured out that the sun really wasn't anywhere near the center of the galaxy. And he was able to deduce this by looking at globular clusters. He figured that, well, if we are near the center, then the distribution of these globular clusters ought to be pretty uniform. But instead of them being uniform, it turns out that most of them are located in the direction of Sagittarius. So Shapley said, well, that logically ought to be where the center of the universe is, and we are really not near that if the distribution doesn't look evenly distributed to us. And so he correctly deduced that not only were we not near the center, but that the center of the galaxy is towards the direction of the constellation Sagittarius. In modern times now, we know that the Milky Way Galaxy is sort of mind-bogglingly large, 30 kiloparsecs. So that is about 100,000 light years. So in other words, if light were to travel from one edge of the Milky Way to the other, it would take it 100,000 years to transverse that distance, which is pretty amazing. We also know that, as Shapley had deduced, we are located not at all near the center of the galaxy, but about 8 kiloparsecs out from the center in one of the spiral arms. And the Milky Way Galaxy has a bunch of these spiral arms that you can see depicted here. We also know that although the general shape of the Milky Way is a disk, it isn't without any other substructure. Surrounding the disk is a halo, and in the center of the disk there is a bulge where the most dense region of the galaxy is located. Another interesting thing about the different regions of the Milky Way Galaxy is that they tell us something about the ages of the stars on average, as far as where they are located. When you are looking at stars in the disk and the spiral arms where we are located, these are the younger stars. And if you look further out, in the halo region or the bulge outside of the central bulge, then you're looking at the older stars, which we call population 2. That's a little confusing to me because I would think that I would want to call the younger stars population 1 and the older stars population, I would think I would want to call the older stars population 1 and the younger stars population 2, but it's actually the reverse. So try to keep that straight in your mind. It often confuses me, and I have to think about that. Anyhow, one thing that is true about younger stars versus older stars is that the younger stars generally have a higher composition of metal content. And by metals, astronomers mean any element heavier than helium, which is probably laughable to some chemists. But basically, the idea is that the older stars, when they formed out of the gas and dust of their stellar cloud. But at that time, when they formed, the universe was consisting mainly of hydrogen and helium. So there wasn't really a whole lot of heavier elements that they could form out of. So that ends up being their composition, mainly hydrogen and helium. Then when those larger stars from that population die in a supernova explosion and spew out all the heavier elements into the interstellar space, then those heavier elements can get incorporated into younger, newer stars, the next generation of stars. And so this is why younger stars are found to have heavier elements in addition to hydrogen and helium. Now, don't get me wrong, they are mostly hydrogen and helium, but they still have those heavier elements within them that the older stars do not have. They are what we would call metal poor. And there is some thought that you kind of need that metal content in order to form planets, especially rocky worlds like the Earth. How could a budding solar system form out of a cloud which is mostly hydrogen and helium. You're not going to get any rocky terrestrial worlds out of such a thing. You need a younger generation where there are heavier elements that can condense into planets like the Earth. So this chart just summarizes a little bit about the two different populations in the Milky Way and where they're located. And so I mentioned the spiral arms a few times. The Sun you see here in this chart in the Orion Cygnus arm, and there's our neighboring arms are the Sagittarius arm, which is closer in towards the center of the Milky Way, and then the Perseus arm, which is a little bit farther out. And you can think of these as sort of compression waves. You know, if you're driving along the highway, sometimes you get a little compression of traffic, and then you make it through that congestion and it's smooth sailing for a while, and then you hit another congested area. This happens a lot in nature, and it also happens with galaxies like the Milky Way, where there are these denser regions and they are in between them less dense regions. So how did the Milky Way get to be the way it is with the stars that it has? Well, since we know the older stars are in the halo and the bulge, then we know that it must have started out as a pretty large region, more like what is shaped like the halo. And from there, it's a similar idea to star formation, where this huge intergalactic cloud this time, instead of an interstellar cloud, starts to rotate and condense, and the central bulge part is going to form first. Meanwhile, some of the stars are living out their lives and dying in supernova explosions and spilling out other gas and dust into the into space that other stars can form out of. And so then eventually, as it continues to spiral and condense into a disc-like shape, then the younger stars are going to form in that disc shape, because now most of the cloud surrounding the larger part outside of the disk is already dissipated, and that's the only thing left there are the older halo stars and globular clusters. So this slide is entitled pretty dramatically "Galactic Cannibalism," but really the thing that to keep in mind is that galaxies do interact with one another sometimes. It isn't the case that they develop in isolation and never encounter another galaxy. Sometimes they come close enough to gravitationally interact, and in that process, if it's kind of like cars wrecking. Sometimes if they crash into each other, they're going to deform. Both of them will end up deformed. Or if it's a very large galaxy, maybe it will entirely total the smaller galaxy, kind of like a huge truck totaling a little car. And in the case of galaxies, it might just incorporate that galaxy into itself. That's the idea of galactic cannibalism. And so when this happens, though, it's very important to realize that although this seems dramatic, galaxies colliding with one another, I should use the term colliding lightly, because there's no actual collision of stars themselves. It's just the gravitational influence of the galaxy itself and the shape of the galaxy getting deformed. I almost like to think of it as smoke rings, and one colliding with another would probably warp the way they're shaped, and instead of a ring shape, maybe it would just dissipate into an S-like shape, or they would, somehow come together into one shape that is no longer a ring. But in that process, it's probably unlikely that any individual atoms of the smoke collided with one another. Okay, so maybe that's not a perfect analogy, but that's kind of how you want to think of it, because the space between each one of these stars, although from far away it looks like they're very densely packed, they are not very densely packed. So none of the stars are actually going to collide with one another. Their region of space gets warped, and sometimes instead of being shaped like a spiral arm, they're now shaped like an ellipse or something else. Okay, and incidentally, the Milky Way Galaxy and the Andromeda Galaxy are on a collision course with one another and will eventually have some kind of interaction like this. So what's going on in the galaxy besides stars? Well, in between the stars, there's empty space, and then there's also gas and dust. As you know, that's what our stars and planets and whatnot form out of. And this dust is dustiest along the disk because that's where most of the matter is located. So this picture here shows you the Sombrero Galaxy, and we happen to be looking at it edge on. Okay, so perhaps if we were to look at the Milky Way, it might look something similar to this if we could step outside the Milky Way and look towards the center with us looking towards the edge. And some clouds actually heat up because of nearby stars, and they can actually give off radiation then, instead of, we think of them as cold and more like absorbing radiation. But if they become excited and heated, they can actually give off radiation, and this is called an emission nebula. Another weird effect that can happen is what we call a reflection nebula, where the light sort of reflects off of the dust in an interesting optical way. And then you see that it's sort of blue in this image here. And of course there's the opposite of, well, I don't know if it's the opposite, but it sort of looks the opposite of an emission nebula, and that would be a dark nebula, which is just, as the name implies, dark. And so instead of giving off light, it just sort of blocks the light, and you can't really see any star's light that shines through that region. And just like we can tell something about the composition of stars from their spectra, we can tell something about the composition of interstellar clouds from their spectra as well. And from the spectra, we've been able to realize that most of these clouds, not surprisingly, are composed of hydrogen and helium, just as you might expect, because this is what, if the clouds are large enough and they undergo certain set of circumstances, this is what stars will form out of. And so one other thing that can occur due to the presence of interstellar gas and dust is that the light we receive may actually be a little bit shifted from what it should look like. Now, we talked about redshift in terms of a Doppler shift. Now, that's due to the motion of a star, but we can also get a reddening effect by the fact that the light leaving the star is, some of it's diverted inside the cloud of gas and dust, and so the blue light is more diverted or scattered for the same reason that the sky is blue. And so more red light comes out of the star because more red light emerges from this cloud than does blue light. Okay, so this effect has to be accounted for too when we're trying to determine what the redshift is of a different star. But in general, most of the interstellar gas is fairly cold, and so it doesn't really emit very much in the way of radiation. Sometimes when it is able to emit, it's going to emit, since we're talking about hydrogen, it turns out that a favored emission is this 21 centimeter radiation emission. And that should sort of make sense to you because that's in the radio wavelength. And we're talking about very cold space, very cold gas. And remember that when we were studying black body radiation, we were able to understand that the hotter an object is, the bluer it is. And that was Wien's law that told us that. So the opposite of this would be the colder the object, the longer the wavelength, or the redder it is. So once you go redder than red, you go to infrared, and once you go redder than that, you go to microwave, and then redder than that is radio. So that's why this radiation is such a long wavelength, and it's only detectable really by radio telescope. We can't actually visibly see it. So what is the Milky Way doing? Is it just static? Of course not. It's actually moving. Remember when we were talking about Keeler and his contributions here in Western Pennsylvania to our understanding of Saturn's ring and how it was made out of particles. When we discussed that, we talked about the fact that if the ring had been a solid disk, it would rotate in a different way than if it was made out of particles, which each followed an orbit similar to the planets orbiting the sun. And so Keeler was able to use that information to deduce that the disk, Saturn's disk, was actually not a disk. It was made up of tiny little particles, lots of particles. So astronomers naturally, maybe they want to understand, well, what's going on with the Milky Way? Things are moving, they're rotating around the central bulge of the Milky Way, but how exactly are they rotating? Well, it probably is pretty obvious that it's not a solid disk. We're not attached to other stars in a solid disk-like way. So the next logical thing would be that you would expect that the stars of the Milky Way would orbit the center of the Milky Way similarly to how planets orbit a star. That's very logical, and it would be the next best guess if you had already ruled out that the Milky Way is not a solid disk. Well, what's very odd is that it doesn't turn out to be like that at all. The stars which are farther away from the Milky Way center are orbiting about as fast, or sometimes even a little bit faster, than stars that are closer in. So that's almost backwards of what we would expect. It's certainly not at all what we would expect if the stars were acting like planets orbiting a star. So how exactly does that work? Well, what we can do is try and figure out, well, let's just blindly say, let's figure out what the mass is of the entire galaxy. And, we can make some estimations to figure that out based on how fast we are moving and, what we observe, what we guess to be the radius of where we are from the center. And when we do that, we come up with a mass measurement which is tremendously large. basically, this mass doesn't agree with the mass that we see. The lights from all the stars do not add up to the amount of mass that would be required for us to have the orbital speed within the Milky Way that we have. So if that's the case, then where is this additional mass? If we cannot see it, if it's not visible, even if you account for things that are invisible, such as planets that don't give off their own light, or black holes, objects that you're not going to actually see, even if you account for that, it's still far too little mass. So the only thing that scientists have come up with to explain this is the presence of dark matter. And so this dark matter is thought to pretty much surround the Milky Way galaxy and account for the extra mass that we don't see. As I mentioned earlier, even though when you look at a galaxy from far away, it looks as though the stars are very densely packed. They really are very far apart. 1 star per 10 cubic parsecs. So that's really a lot of space in between each star. Now, it is more dense at the core of galaxies, and at the very core, most galaxies, including the Milky Way, are thought to have a supermassive black hole. And we have X-ray, gamma-ray observations to confirm the presence of that black hole in our galaxy. And this is an image of where the supermassive black hole is thought to exist. So one last topic here we talked about spiral arms, and we talked about how they are sort of, you can think of them as compression waves or density waves, but what implication does that have for star formation itself? Well, the interesting thing is that, if you have an interstellar cloud of gas and dust just hanging out between 2 spiral arms, it's not doing much of anything. But perhaps it drifts towards a spiral arm, and suddenly there are many more stars gravitationally influencing it. And this is when the cloud responds by starting to compress and collapse, and then eventually this happens enough that stars can form out of that cloud. And then, the bluer stars eventually supernova and leave the arm, and this is the process that sort of repeats. And also with different galaxies, it's interesting to look at their star formation rate. That's another measurement we can take, but we'll get into that more when we talk about other galaxies. But that about wraps it up for the Milky Way galaxy.